completely different boiling points. Right, so I just want to check that everybody can see the screen. So can someone shout at me? Can you see those two molecules there?
Yes.
Thank you. Right, I can hear people. Oh, that's so reassuring. Right, so this one is called propanone. And you don't need to worry about that just yet. But we need to see why this molecule here, A, and molecule B have got profoundly different boiling points. So if anyone wants to type in why A and B might have different boiling points. So why is A's boiling point much lower? That's the temperature at which it turns from a liquid to a gas. Why A and B have got profoundly different boiling points. Any ideas out there? So if you want to type that into the text box, anyone out there got any ideas why they might be profoundly different? Looking at the number of bonds, potentially. So thank you, Maddie, for that. Anybody else? Franek, because one's got an unsaturated bond. I'm liking the ideas. I'm liking the ideas coming here. Anyone else? Hey, Annabelle, you've hit the nail on the head. So Annabelle says A has weaker intermolecular forces. So thank you, everyone else, for your contribution. But Annabelle has hit the nail on the head. It's to do with forces of attraction between molecules and not the bonds inside them. So when you boil a liquid, you do not break these strong covalent bonds. So it's nothing to do with the bonds inside them at all. It's to do with force of attraction between molecules, and these are called intermolecular forces. Now, today I said I would demonstrate some bendy water, which I'm going to do in a bit. But what we're going to do before I show you my bendy water thing, just go on to get rid of those, is let's look at those intermolecular forces. Now, we've already met the fact that molecules are polar. So this is a nail polish remover called propanone. So it's nothing to do with the internal intramolecular. So that carbon double bond oxygen is intra. So he's not breaking them. It's inter. They're the forces between two molecules. Now, I refer to these as like doggy, like one molecule sniffing another molecule. And you know that these dipoles exist, these polar bonds exist because of a difference in electronegativity between two atoms. So this molecule has a dipole, so we say it's polar, and this other molecule has a dipole, and that's polar. So they permanently attract each other. So they've got what's called a weak intermolecular force of attraction. So Annabelle was absolutely spot on. It's to do with the intermolecular forces of attraction. Now, what I would like you to do in a moment, because I'm just going to get my bendy water thing and get the camera set up for it, is this here says a dipole-dipole attraction exists between these two molecules. And therefore, if we just look at one propanone molecule and then we heat it up, as we heat it up, those intermolecular forces are broken because as energy goes into anything, electrostatic forces, the bonds start to vibrate and then break apart. So these aren't bonds per se, these are intermolecular forces. So whenever you're asked about why molecules have different boiling points, it's to do with intermolecular forces. You're not breaking internal bonds within the molecule. You're not breaking internal bonds within the molecule. Okay, so there's a gang of molecules, propanone molecules, with these dipole, what are called permanent, because these are permanently polar. These are permanently attracting each other. So what I'd like you to do is just quickly, on a bit of paper, just sketch those attractions. I'm just going to give you a couple of minutes to sketch those attractions just while I get my bendy water experiment. So could you just sketch that on a piece of paper? Because a picture paints 1,000 words. I'm just going to leave that on the screen for a second. I'm just going to take my camera off, and I'll put that back on the screen in a minute. So 1 second. Right, so it doesn't distract you. So could you just make a diagram of those dipole attractions there? I'll be back in a second. Okay, so what I'm going to do now is I'm going to blow up a balloon. So I'm just going to see if I can see myself. I can't even see myself on the screen here. Okay, there I am. So I'm going to blow up a balloon, and then I'm going to switch my camera to my iPad, which I'm going to do right now. So here we go into the class meeting. Just a moment. There we go. So I'm going to present my screen from here. There we are. Right, so I've got a balloon. And I'm going to put my camera onto my iPad now, which will come on in a minute, if this works. It's coming on in a minute. Here we go. Right. Right, so this is a balloon. And here I have a burette next to me, and here's a balloon. Right, hopefully this works. So I'm going to blow my balloon up. There we go, there's a balloon, you can see me twice. Right, so what I'm going to do is, from the burette that I have here, so I've just pulled that back a little bit. So I've got a burette, and in the burette is some water. And what I'm going to do is I'm going to rub the balloon in my hair to create some electrostatic or static electricity. So that's electricity that's not moving, that's charged. If I rub it in my hair, and let's see if it's working. You can see it's pulling my hair. And what I'm now going to do is I'm going to allow the water to run into the beaker like that. If I bring this up to it, you can see, hopefully, that the water starts to bend towards the balloon. Okay, and that is because, try that again. I just like doing this. And that is because the polar nature of water, because water's got these permanently polar bonds. So I'll do it again so you can see it from a different angle. Just like doing this. You can try this at home. There you go. So the water, the stream of water is actually bending towards the balloon. So that is because water is a polar molecule. So I'm just going to stop on my iPad because it's really, really slow on there. Get that off and stop presenting and come back to you guys. Right, so that's bendy water, and you can try that at home, and it's because of the permanent dipole that's present in water. So if we now go back to the PowerPoint again, let's go look at those two molecules again. Now, Annabelle said that the intermolecular forces between the ethanol molecules are greater than the intermolecular forces of attraction between the propanone molecules. So if you've got nail polish remover at home, pour some on your hand and wave it about. It'll feel really cold. If you pour some vodka on it, it won't feel as cold. If you pour water on it, it won't evaporate as quickly. Whereas the propanone, and if you were in the lab, I'd pour some on your hands and you realise that the liquid isn't there anymore. Because what in effect you're doing as you're warming up the propanone molecules, the force of attraction between the two propanone molecules actually breaks. So you're not breaking these bonds. So never ever say ever again that it's got more bonds or it's got stronger bonds, because you're not breaking the bonds. Because if you did, when you boiled a kettle, you would get hydrogen and oxygen coming off. So these little hearts that I've got there are intermolecular force of attraction, and they're called permanent dipole. They're quite weak, and as soon as your body temperature, which is about 36 or 37, you pour some on your hand, it will easily break those forces of attraction, and then they'll turn into a gas. So when something boils, it turns from a liquid to a gas. This is the most important factor that you need to write down in an exam. If you're ever asked to explain why one substance has a higher boiling point than something else, you would say more energy is needed to overcome the intermolecular forces or the forces of attraction. So that's for breaking anything, for breaking any electrostatic attraction. Energy is needed to overcome it. So let's now go and look at our ethanol molecules. Now, I'm sure none of you have ever drunk anything with alcohol in your lives. I'm absolutely certain that you haven't done that. So you won't know what it's like to experience a hangover at all, will you? So let's see how hangovers occur. Well, first of all, here's two molecules of ethanol. Now, this intermolecular force of attraction here, as Annabelle said, is far stronger than the permanent dipole attraction between the propanone molecules. And this is a special type of attraction. What we've got going on here is this hydrogen atom here is directly covalently bonded to an oxygen. And oxygen atoms next to fluorine are really, really electronegative. They've got an electronegativity value of 3.5. And therefore, the difference in electronegativity is that an extra strong dipole is formed such that this poor hydrogen here is having its electrons pulled back by the oxygen, and it's almost a naked proton. Don't say it is a naked proton, but this is what it says in the textbooks, almost a naked proton. Remember, hydrogen is simply a proton and an electron. And if this oxygen's pulling electrons back, it's almost a naked proton. Now, on a neighboring propanone molecule, ethanol molecule here, the stuff you drink in vodka, you've got an oxygen with an unbonded pair of electrons. Yesterday we were looking at shapes, and we know that oxygen's actually got 2 lone pairs. Should really put the other lone pair in just to be pedantic. So it's actually got 2 lone pairs. But the hydrogen embeds itself in the lone pair of electrons on this oxygen atom. And that extra strong intermolecular force of attraction there, so as the oxygen is embedding itself in the lone pair of a neighboring alcohol molecule, this extra strong dipole-dipole attraction arises. And it's much stronger than an ordinary permanent dipole. And this is actually called, so this extra strong dipole-dipole attraction is also known as a hydrogen bond. Now, the word bond is really misleading because it's not a bond in the conventional sense of a covalent bond or a dative covalent bond. It's much weaker, but it's stronger than an ordinary permanent dipole. Now, if in an exam you're asked to describe a hydrogen bond, you must draw a picture. Because if you start as well as using the words, because you can use the words, you can label your diagram, and that is the best way of describing hydrogen bonds. So in liquid alcohol or ethanol, you've got these extra strong dipole-dipole attractions, and when you heat up the ethanol to 77 degrees, then they turn into a gas. So what's that got to do with a hangover? Well, if we look at the structure of ethanol, again, if we were to draw out the structure of ethanol, we've got an oxygen atom with a hydrogen atom, and you've got a permanent dipole where this oxygen is extremely electronegative. Therefore, it's almost a naked proton. And there is the rest of the alcohol molecule, which I'm just going to call R for the rest. So this bit here is just the rest, because it's getting in the way. It's hurting your eyes because it looks, you're not used to seeing that. Now, if you drink alcohol, if you drink ethanol, then just imagine it's got this lone pair of electrons, that electron deficient oxygen. In your brain, so let's draw someone's head with my mouse. So there's someone's brain after having a few drinks. There we go. There's a nice smiley brain. Okay, so you've had a few drinks, looking a bit worse for whatever. Okay, so there's your brain. I'd normally do this on the board a lot better. Right, so let's do some red eyes. So in your brain, yeah, I've had a few drinks, a few too many. Right, so in your brain, it's protected by a membrane, which is basically a layer of fluid or what, which is mainly water, and that is in between 2 membranes, sandwiched between 2 membranes. Now, if you've got alcohol in your bloodstream and you've got water in that membrane, water molecules, so let's draw a water molecule. Also, as we just saw from my bendy water experiment, also have a very strong permanent dipole, because the hydrogen here is attached to an extremely electron deficient oxygen, and therefore it's also a very naked proton. And it will embed itself in the oxygen of a neighboring alcohol molecule. So guess what? Alcohol and water love each other a lot. And therefore, if the blood your blood contains a lot of alcohol, and remember the bloodstream's passing over your brain, it will start to absorb water from this cavity, and therefore the two membranes are going to start to rub together and you're going to get a rotten headache, and that's what that's caused by. So water molecules can hydrogen bond with alcohol molecules. They like each other a lot because they're both very polar, and they can hydrogen bond together. So you don't just get alcohol molecules hydrogen bonding with each other, you can also get water and alcohol hydrogen bonding together. So hydrogen bonds are called bonds, but they're very strong dipole-dipole attractions. If you're asked to describe them or explain why alcohol has got a very much higher boiling point, energy is needed to overcome the intermolecular forces between the alcohol molecules. But what are those intermolecular forces? They're very strong dipole-dipole interactions, which we call H bonds. Now, you're going to meet them in biology, you're going to meet them next year in chemistry. They are all around us, and without hydrogen bonds, life on Earth wouldn't exist as we know it today. So I'm just going to look at some examples of hydrogen bonds. So if you were to go outside and it's a freezing winter's day, so last year I dug a pond in our garden, and I was really amazed to find that my little beautiful 8 goldfish, there was still 8 goldfish there at the end of the winter. And that is because of hydrogen bonding. So there's my pond in the, I can't draw my little goldfish in it. Okay, I'll draw a goldfish. So all 8 goldfish were still swimming around in the summer. And that is because of hydrogen bonding. Because in the winter, the water freezes and turns into ice. And ice is less dense than water. So water actually freezes from the top downwards. So in the winter, the layer of ice on the top protects the little fish at the bottom, because it's actually warmer at the bottom because there's a layer of ice on the top. And that is because of hydrogen bonding. And we'll look at some diagrams of that later. So if you're ever asked why water has got such a high boiling point, it's because energy is needed to overcome the hydrogen bonds between the alcohol molecules or water molecules or whatever hydrogen bonds. So if you're in the class on your whiteboards now, I'd get you to write this down. But just for today's purposes, so it's permanent dipoles attractions. Are they larger or smaller? So Renee, are you out there? Can you hear me, Renee? He's not talking to me. Let's see who's out there. It's gone very quiet. You might all have just gone. Right. Yay, he's there. Right, so Renee, which one is larger? Here we go. Oh, I've got to give you the answer now. So are dipole-dipole attractions weaker or stronger than hydrogen bonds, Renee? Fantastic. Right, we've got some life out there. So hydrogen bonds are weaker. So obviously more or less energy, Maddie, is needed to overcome them. Should I? More or less. Excellent. Yes, I'm getting some feedback. Yes, less energy is needed to overcome them. So even though propanol and ethanol have a number of electrons and therefore the same strength, and we're going to look at those later, what are called van der Waals forces, propanol has a much lower boiling point. So whoa, we've answered a question on comparing boiling points. So your answer would be the same bog standard answer in any case when you're asked to compare the boiling points of two substances. You compare the attractions, so dipole, what are called permanent dipole-dipole attractions. Permanent dipole-dipole attractions are weaker than the hydrogen bonds. We've talked about comparing the two attractions. Less energy is needed to overcome them, even though they have the same number of electrons. So we're going to look at these weird van der Waals forces in a bit. So propanone has a much lower boiling point. So again, this topic is quite easy to understand, but it's how do you communicate your answer succinctly? And I'm going to say again, a picture paints 1,000 words. So if you can do a diagram, you can draw a diagram showing a hydrogen bond. If you can do a diagram showing a dipole-dipole attraction, then label it and just say less energy is needed to overcome, that's break, dipole-dipole attraction. That will explain the difference in boiling point. So let's now look at that last intermolecular force. But before we do that, let's just compare 4 molecules. This is the propanone one, the nail polish remover. This is ethanol, the stuff that's in vodka. This one here is what's called an aldehyde, and this one here is something called a carboxylic acid. So don't worry about the organic chemistry of them. But we've got these molecules. And let's compare, we've already compared these two, first of all. And that boiling point should say plus 44. We've compared these two, but what about these 2 molecules here? These 2 molecules here. They have got identical numbers of electrons, and they've got almost identical molecular masses. And yet this one boils at 56, and this one here, propanoic acid, boils at 141. And your answer would be why they're substantially different is this one has permanent dipole attractions between molecules, but this one, because it's got an oxygen joined to a hydrogen, the hydrogen is almost a naked proton, so that one can hydrogen bond. So how do we know if something can hydrogen bond or not? Okay, how do we know, if something can hydrogen bond or not? Are you listening for the rules? To work out if something can form hydrogen bonds with something else, the hydrogen atom has to be attached to either a nitrogen or an oxygen or a fluorine, because those are the 3 most electronegative elements in the periodic table. And if hydrogen is directly joined to any one of those, its dipole is such that the hydrogen is almost a naked proton, and therefore it will seek out a lone pair on the neighboring, somewhere on a neighboring molecule. So it's a lone pair hunter. So it'll go out looking for a lovely pair to embed itself in. Okay, so if you see a molecule where a hydrogen is joined directly to an oxygen, a nitrogen, or a fluorine, then it can hydrogen bond. So that can hydrogen bond, and that can hydrogen bond because the hydrogen is joined to an oxygen. That can't hydrogen bond, and that can't hydrogen bond because the hydrogen isn't directly joined to an electronegative atom. All these have is permanent dipole attractions. So remember this for our quiz later on. Remember this for our quiz later on. I'm going to be asking you some questions on. So if you see in your molecule, the hydrogen's joined directly to a nitrogen atom, an oxygen atom, or a fluorine atom, you're going to get hydrogen bonding. This, and I must say really strongly, this here is not the hydrogen bond. Oh, let's go back. This is not the hydrogen bond. This is a strong covalent bond. That's not the hydrogen bond. The hydrogen bond arises when this embeds itself in the lone pair of another molecule. So the yellow highlighter is the hydrogen bond. These things here are strong covalent bonds. Right, let's look at the last intermolecular force of attraction now. So in this, we've got a series of molecules. Now, I've given you a booklet called Alkanes, and we're going to be looking at that on Friday. And you may have met alkanes at GCSE. These are simple hydrocarbon molecules where you're getting an increasing number of carbons. And as we look at the number of electrons, now what do we mean by the number of electrons? Well, let's draw a molecule of methane, the simplest one. So methane is CH4. And if we count the electrons in this molecule, hydrogen has got 1 electron. 1, 2, 3, 4. Carbon has got 6 electrons. So the total number of electrons in there is 10. The next one along, ethane, that we'll be looking at more in the alkane series later on. Ethane, if we count the number of electrons, each carbon's got 6, that's 12, 13, 14, 15, 16, 17, has got 18 electrons. So why are we looking at electrons? How is that even affecting the boiling point? Now, if we were to plot a graph of each carbon, so number of electrons, so that's methane. I'm going to call that carbon number with 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5, and so on. The energy needed to overcome the force of attraction between molecules increases. And how can a force of attraction arise between 2 methane molecules when there's no dipole? There's absolutely no reason on earth why one methane should be attracted to another. And in fact, you know it isn't. Because you know when you let out an eruption of methane, it's a gas. You know when you turn on the tap, it comes out as a gas. And gases mean that there is no intermolecular forces of attraction. So that's why methane is a gas at room temperature, because there are no intermolecular forces of attraction at room temperature. But we can compress these gases. So when you go camping and you have your propane gas, it boils at minus 42, but when you push the molecules together in your gas canister, in fact, the methane, so there's your gas canister, your propane in there is actually a liquid because you can hear it, because you've compressed it. So you're forcing the molecules to become attracted. So if you push them close together, they will become attracted. So there are some short range, as soon as you push them close together, forces of attraction. So let's look at those forces of attraction now. So what our hypothesis from this is going back to a misconception. I'm just going to get rid of my, let's get rid of these things. A misconception before was A. So the big misconception that we must iron out, we definitely must get rid of. It's a big one, even amongst some A-level students and adults. What is causing that trend? Why is there an increase in boiling point? Is it A, there's an increasing number of bonds between the carbon atoms? Or is it B, there is increased shielding from the carbon nuclei? Or is it C, as the molecules increase in size, there are more electrons. So I know you're out there ready to type in your answer, because you all know now it's definitely not A. Because remember, when you boil something, so here's your propane with 3 carbons, you do not break those very strong covalent bonds. So when you boil your camping gas, when you turn the gas on, it's just that the liquid molecules that are attracting each other separate out. You're just separating that from that, and you're breaking these intermolecular forces. You're not breaking bonds at all. When you boil something, you do not break bonds. The answer to why this boiling point is increasing, why more energy is needed to overcome forces, there's something called instantaneous induced dipoles, and we're going to look at those in a minute. So we call these instantaneous induced forces van der Waals forces, and they exist between every single molecule. Every molecule has van der Waals forces. So let's have a look at van der Waals forces. What are they? Okay, right, so let's look at this diagram here. Here we've got a simple atom. This could be even a noble gas. There is no attraction between these at all. However, when 2 atoms get even slightly closer than 5 nanometers, that's 5 times 10 to the minus 9 meters. So a nanometer is 10 to the minus 9 meters. So when they get that close, so you put them in your gas pressure, your camping gas bottle, and you put them under lots of pressure, then what will happen is, if they get close, at one point in time, this nucleus here in the normal atom, when it's not brought close to another one, or in a normal molecule or anything, you've got this even distribution of electrons in an atom or a molecule. However, if you bring them close, you will get maybe an instantaneous, one point in time, distortion in charge. And this atom here, or molecule, could become slightly negative. Now, that dipole there only exists for a split second in time. We call it an instantaneous dipole. That, in turn, repels all these other electrons backwards on a neighboring atom or molecule, and that part of the molecule now is induced. So the dipole is induced. So an instant dipole induces means creates a dipole in this other atom or molecule, and that becomes slightly positive. So that's called an instantaneous induced dipole. This happens in all atoms and molecules if they get 5 nanometers or closer. So it's very short range. But now, if you have a slight negative and a slight positive, even for a short amount of time, you have an attraction. And that is called a van der Waals, or some books call them London dispersion forces, and they exist between all molecules and atoms. So this polarity, which doesn't last for long, so it's called an instantaneous induced dipole, exists between all molecules. Now you can see here the electrons. These are the negative charges. The more electrons are in a molecule, the greater this effect, the greater this instantaneous induced dipole. Because you've got now loads of electrons being induced to move over to the other side. So the more electrons there are here, the more repulsion the electrons feel here and move over. So you're now creating this attraction. So the more electrons something has, the greater the van der Waals forces. This is what you need to be able to know. So if you've got a pen and paper, I say this PowerPoint's staying up. But the important thing to notice, as molecules increase in size, there are more electrons, so greater instantaneous induced dipoles. And that is all molecules. So these are called van der Waals forces. So you can say instantaneous induced dipoles. That means exactly the same as van der Waals forces. So van der Waals forces also increase. So more energy is needed to overcome these attractions between molecules. So as molecules get bigger, there are more electrons, and therefore the van der Waals forces increase. So that explains, if we go back to our trend here, so here we can see the number of electrons is increasing, and therefore the melting point and boiling point. So butane boils at 0 degrees Celsius, whereas methane, the stuff that comes out of gas taps, boils at minus 164. So we can conclude that methane has got weaker van der Waals forces between the molecules. So this is the important thing to know in the yellow box here. So as molecules increase in size, there are more electrons, so greater instantaneous induced dipoles. Van der Waals forces increase, so more energy is needed to overcome these attractions between molecules. So these happen, these are the only intermolecular forces, in non-polar molecules. So they exist between all molecules, polar and non-polar, but they're the only forces of attraction between non-polar molecules. So remember, when we talk about a polar molecule, it has to have a dipole in it. So the only force of attraction between non-polar molecules. So it's called an instantaneous. That just arises at one point in time, becomes slightly negative, and that induces a dipole in a neighbouring molecule. So here's our methane molecules all wandering around, and it's not until you compress them, so you can see these two guys here have come within 5 nanometers of each other, and a dipole is induced. So if you put a gas under pressure, you reduce the temperature, you take the energy out, the molecules get close together, you will get van der Waals forces, and you will liquefy your gas. If you're able to increase the pressure even more and reduce the temperature even more, eventually your gas will solidify. Go, how can that be? Well, you know, if you boil your kettle, you get steam. But if you cool and condense your steam, you get water. And if you put your water in the fridge, you get ice, which is solid steam, because you've reduced the temperature. You've taken the energy out. The molecules get close together, and therefore you're increasing the number of intermolecular forces. Right, so now we've got a little quiz. The little quiz that we're going to do now is on here. So if we go to our stream, and I'm just going to download this so you can see it on full screen. It's coming up now. Right, so what you have to do, and it's not very interactive, you're just going to have to shout out to yourself and see if you get it right or wrong, because I want to get you to do some written work. Okay, so we've got 3 molecules here, and one of them is ammonia. Now, this is where what you met yesterday actually influences what we're going to learn today. We just said that if a molecule has a dipole, then it's going to have a dipole-dipole attraction. But just to remind you that if the hydrogen is joined directly to an electronegative atom, then you're going to get hydrogen bonding between those molecules. Okay, so let's look at 3 molecules here. We've got ammonia, methanol, and octane. And we need to decide, are the forces between these molecules hydrogen bonds, just permanent dipole-dipole attractions, van der Waals, or none of the above? So I'm going to walk you through this and you're going to go, did I get that right or didn't I? I'm not going to ask for audience participation in this. I'm going to leave this up in case you don't get it. So ammonia, you're all screaming at me, Wendy, that's hydrogen bonding. Why? Because if we look at the nitrogen, it's got hydrogen directly attached to it. And therefore, because it's got that directly attached to it, this hydrogen here is almost a naked proton. Almost a naked proton. And trying to get a pen up here. So it's almost a naked proton. And therefore, it would embed itself in the lone pair of a neighboring nitrogen atom on another ammonia molecule. So there it is. So hydrogen embeds itself in that lone pair of a neighboring ammonia molecule on the nitrogen atom. So that's hydrogen bonding. Now, which one is methanol, you may ask? Is it dipole-dipole, van der Waals, or none? Well, you can see that methanol has got an oxygen, which is delta minus. So it's definitely got a polar bond, but the hydrogen isn't joined directly to it. So it's polar, but it's not hydrogen bonding. So you are correct. Well done, those of you out there who are watching this. It's definitely dipole-dipole. Now, octane has got carbon and hydrogens. And when you go to look at your electronegativity tables, which I know you've got directly in front of you, carbon and hydrogen have almost no difference in electronegativity. So alkanes, we say, are non-polar. There are no polar bonds in there. However, you can see that there are definitely going to be loads of electrons in octane because it's a big molecule. So you would predict that octane is a liquid because of the van der Waals forces between the octane molecules. So let's look at the next slide. So what I want you to do now is, if I tell you the names of these things, I want you to be thinking on a piece of paper again. And if you were in the class, I'd get you to write this down. But I want to move on to the written work in a minute. So I just want to see if you can test your own understanding. So which intermolecular forces exist between 2,3-dimethylbutane, sulfur, and phosphorus? So which ones do you think it is? So I'm just going to escape from that a minute. Okay, I'm just going to make that small. Over here, I'm going to get rid of that. Ah, it's disappeared. Sorry, it's up here. Right, so which one? And I can see you guys now. So which one is 2,3-dimethylbutane? So I'm now going to go to the class. 17 people in there. You can simply type in or you can open your mic. Okay, so my thing's disappeared again. There it is. So Alex, what do you think 2,3-dimethylbutane is? Is it H bond? Just write DD for dipole, V for van der Waals, or none. What do you think, Alex, for... It is V to V. Well done, Alex. It is van der Waals. Excellent. And what about sulfur? What about sulfur? Let's have a look in there. Alfie, what do you think the intermolecular forces between sulfur is? You can type it in or you can say. He's dead speak. Right. Annabelle, do you agree with Alfie? Alfie said dipole, dipole. Annabelle, what do you think? She said dipole as well. Let's go to Ben. What do you think for sulfur? Ben, what do you think for sulfur? Ben said dipole as well. Let's ask Franek, what do you think for sulfur? You can speak or you can type it in. None. Right, let's see what Georgia thinks for sulfur. What's the force of attraction between sulfur molecules?
Is it van der Waals?
Brilliant! You are correct. You're the only correct one so far. Georgia, could you explain your thinking as I cuddle my balloon? So why do you think it's just van der Waals?
Because I don't know.
What did we say on the last slide? Anyone out there want to help? Why is it just van der Waals? Anyone out there?
Is it because it's non-polar?
Brilliant. It's non-polar. Who said that?
Lucy.
Lucy. You are correct, Lucy. There is no difference in the electronegativity between any of the sulfur atoms. So it has to be van der Waals, because if a molecule is non-polar, the only force of attraction is van der Waals. So I'm just blowing up 2 balloons here because I like blowing up balloons. But so if I just see if I can, you guys can see this. Right. So here's one balloon. Here's another balloon. Now they're not attracted to each other. So this is one sulfur molecule. This is another sulfur molecule. But because there's so many electrons, as soon as they get close to each other, oh, they're not doing it now, they will attract. Okay, so they're non-polar, but as one gets close to the other, you induce a dipole, so an instantaneous dipole, and you have van der Waals forces. How do we know it's non-polar? How do we know it's non-polar? Because there is no difference in electronegativity between the atoms. Right, let's do phosphorus. Let's do phosphorus. Which intermolecular force exists between phosphorus atoms? Can you all type in your answer now? Is it H, is it D, is it V, or is it N? H is hydrogen bonding, D is dipole-dipole, V is van der Waals, and N is none. Can you all type your answer in now, please? Yay! Woohoo! You've cracked it. You've cracked it. Yep, because every phosphorus atom within that molecule, look, it's after me now, this balloon. Every single atom in that molecule has an identical electronegativity. So when you bring one phosphorus molecule next to another phosphorus molecule, so that's one phosphorus molecule, if I just make that bigger, and let's just present it and draw a diagram of another phosphorus molecule next door. So they have this like tetrahedral arrangement in the molecule. You're gonna, as they get close, the only attraction that can happen is van der Waals, because they're non-polar, because they've all got the same electronegativity. So van der Waals for 2,3-dimethylbutane, because it's non-polar. Van der Waals for sulfur, because it's non-polar. Van der Waals for phosphorus, because it's non-polar. Right, let's just get out of there and go back to you guys. Now, I'm going to ask you, which one has the higher boiling point? Is it sulfur or is it phosphorus? Type in the box now, is it S or is it P? Which one has the higher boiling point? Is it S or is it P? Can you type in now? And you're all correct. Excellent. Because sulfur's got more electrons. So it's going to have the higher boiling point. It's got more electrons because it's because there's more atoms. So the bigger the molecule, the more electrons, the bigger the van der Waals forces. Let's look at the next slide. Okay, so we've got 3 substances here: water, sodium chloride, methane. So I'm now going to ask one person. I'm going to randomly select one person. So Isaac, are you there? Which intermolecular force for water? You can type it in the box or you can speak to me. Is it H bonds, dipole, dipole, van der Waals, or none? Are you there, Isaac? Which one is it? We're all waiting on Isaac. Is he actually gone back to bed? Looks like Isaac's gone back to bed. Oh dear. Jaden, what do you think? Let's see who responded there. Yeah, so I would like to know where Isaac actually is living at the moment. It's not on here. Right, so water is definitely hydrogen bonding because the hydrogen is directly connected to the oxygen. Right, what about... Oh, right. Right, well, you can do the next one, Isaac. Isaac, which intermolecular force between sodium chloride ions? Is it hydrogen bonding, dipole, dipole, van der Waals, or none? What do you think? Just type your answer in. Is it H bonds, dipole, dipole? So is it H, D, V, or N for none? Which one do you think it is? Nope. Anybody? Let's go to somebody else. See if anyone else can tell me. Toby, what do you think? What do you think, Toby? You can talk to me rather than type it in. Is Toby there? Toby, are you out there? Or am I just talking to the void? Toby! Calling Toby! Hey. Not Van der Waals. I'm afraid it's not Van der Waals. Anybody else out there who I've not asked? I could ask Wendy. Julia, what do you think it is? So it's not H bonds. It's not Van der Waals. Which one do you think it is, Julia? You can type it in. There's only 2 left. You can phone a friend. Hey, she got it correct. Well done, Julia. It's none. And the reason is, if you look at the difference, well done, Julia. If you look at the difference, that's a molecule. These are covalent bonds. These are intermolecular forces. Methane is a molecule, but sodium chloride is a giant ionic lattice. It's not molecules, so it can't have intermolecular forces. It has electrostatic forces of attraction between every single ion. It's not molecular. So well done, Julia. Water hydrogen bonds, because the hydrogen's directly joined. So remember, water molecules then attract each other. And the hydrogen bond is here with another molecule and here. Sodium chloride is none because it's ionic, it's not molecular. And methane is van der Waals because it's non-polar. Right, let's have a look at the next slide. We have hexane, we have trichloromethane, and we have propanoic acid. So let's go out to you guys there. So what do you think? Hexane, trichloromethane, propanoic acid. So let's see who's out there. Let's put the thing back on. So let's go to Jess. What do you think about hexane, Jess? You can speak to me or you can chat. Are you there, Jess? Jess, are you there? Yeah, she is. She said D. What do you think, Lucy, for hexane?
Is it van der Waals?
Could you tell us why?
Because it's non-polar.
Yeah, and can you tell Jess, because Jess was probably not here when we started doing electronegativity, what do you mean by non-polar?
It doesn't have a charge.
There's no difference in slight charge. What causes a molecule to have a dipole? Can you remember, Lucy? What has to be in the molecule to cause it to have a dipole?
Is it oxygen?
Could be oxygen, could be one of the atoms. What other atoms could cause it to be polar?
Nitrogen and
Nitrogen
fluorine.
or fluorine could cause the molecule to have a dipole because they're electronegative atoms and they will cause polar bonds. Well done. So it's when there's a difference in electronegativity between the atoms, and obviously it's difficult to see if you've not got a table of electronegativity, but by rule of thumb, group 7 and nitrogen and oxygen are electronegative atoms. So group 7, oxygen and nitrogen. So let's have a look at the next one. Trichloromethane. Trichloromethane. So going over to Alex. Alex, what do you think for trichloromethane? H, D, V, or N? It is, well done. It's dipole because you've got chlorine's more electronegative than hydrogen, so that molecule is going to be polar. Right, what about propanoic acid? H, D, V, or none? What about propanoic acid? Franek, what do you think for propanoic acid? Franek is out there. Well, which one? You can't sit on the fence. Can't sit on the fence. You were right the other way. It's H. Could you tell me now, looking at its structure, how do we know it can hydrogen bond? You can speak to me. How do we know it can hydrogen bond?
Or is it because hydrogens are like directly bonded to the structure?
Yeah, can you see the hydrogen is directly bonded here? So hydrogen, so that's van der Waals because it's non-polar. Trichloromethane is polar, so it's dipole because the chlorines are slightly more electronegative, and that bit of the molecule becomes delta minus, and that bit of the molecule becomes slightly plus. But with propanoic acid, you've got an electronegative oxygen here pulling electrons away. You've got an electronegative oxygen here, and this poor hydrogen, because it's bonded directly to an oxygen, is so electron deficient, it will embed itself in the lone pair of electrons on a neighboring molecule, so it can hydrogen bond. Right, so I'm just going to discard that. Okay, so there's a few more on here that you can have a look at, but what I want to do now is I want to draw your attention to the questions that you've got in your pack, because otherwise we're going to do no writing. Okay, so remember your pack. Try and ask you. Okay, so can you get your pack out, please? Right, in your pack, there are some questions. Forces between molecules. And on the very first page, there, it's got hydrogen bonding. And what it wants you to do is to draw hydrogen bonding between two molecules. So can you get that sheet now, please? I'm going to start you off. So that you can do this. So hydrogen bonding. And let's just go on to it. So let's draw hydrogen bonding in water. So when you're drawing hydrogen bonding in water, it's really, really, really important. So let's look at ammonia. And can you add to this diagram here? So this is on your Google, this is on the sheets that you were given in class. If you've not got these sheets because you weren't in, just draw the diagrams out for now from the sheets. This is a lone pair of electrons. I don't like the fact they've not actually drawn the 2 dots in there. So can you put the 2 dots in? The hydrogen has got this delta plus, nitrogen delta minus. Can you put the lone pair of electrons in there? So this dotted line here represents the hydrogen bond. Hydrogen bond. It's not really a bond because it's not like a strong bond between two ammonia molecules. Now, what about between water molecules? It's really important you get this right, and I'm going to show you how to draw this now. Yesterday, you learned that water molecules are bent, and that is because of the 2 lone pairs of electrons on the oxygen atom. So put those pairs of electrons on and try and get your bond angle as right as possible. Remember that bond angle is about 105 degrees. So I'm drawing my 2 lone pairs, and it's dead important you put the lone pairs on your oxygen atom. It's then vitally important that you draw the dipoles, that the hydrogens with that little curl, delta plus, because the oxygen is more electronegative, and therefore that part of the molecule is permanently delta minus. Right, to draw the hydrogen bonding on a neighbouring molecule, watch what I do. This is really, really important. You do a dotted line, so there's the covalent bond, and you do it as if it's a continuation of the covalent bond in exactly the same plane. So that angle there should be 180 degrees between the covalent bond and the hydrogen bond. Should be 180 degrees because the hydrogen bond is going to get as far apart from the covalent bond as possible. Then on your neighbouring molecule, your neighbouring water molecule, you draw the oxygen atom. Again, try and get your bond angles as realistic as possible. So from yesterday, we said they're about 105 degrees. And this angle here between the hydrogen bond and this other covalent bond is also 180 degrees. So in effect, you've got these, the covalent bond, the hydrogen bond, and the covalent bond all in a line. Try and get think about your VSPR repulsion theory. So the hydrogen bond will repel as far away apart from the covalent bond as possible. And this covalent bond will repel from that. So your 2 water molecules should be in line like that. It's really important you draw it like that. Now we need to put the lone pair of electrons on your neighbouring water molecule, because the hydrogen here, which is very delta plus, is embedding itself in this lone pair. Now, they've used bunny ears, so we can put bunny ears on ours as well if we want. So there's the bunny ears on our lone pairs. Okay, so it's dead important when you draw. That now describes hydrogen bonding in water. The only thing I've not got on there is your delta plus and your delta minus. So put your dipoles on every single one of those atoms. Okay, so bond angles are right. So that bond angle there is 105 because we learned that Y yesterday, because you've got 2 lone pairs. So I'm going to put my other lone pair on my oxygen. So I've done that with a mouse, so it looks a bit scruffy. Okay, you could also show off and you could put another water molecule here. So if you've not got your sheet that I gave you last week, you should be doing this on paper right now as I'm doing it live. Put your dipoles on. So that's delta minus, that's delta plus. Put your lone pair on. Or lone pairs, because oxygen's got 2 lone pairs. Put your dot, 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 showing the hydrogen bond. Let's label it. This dotty line, because it's not a true bond, is your H bond. This black solid line there is a strong covalent bond. Covalent bond is much stronger than a hydrogen bond. So covalent bond's a proper bond. Hydrogen bond is an intermolecular force of attraction. So water molecules can form 2 hydrogen bonds per molecule. So draw that now, please. Could you draw that now? I'm going to get you to photograph your work and upload it at the end of the lesson. Okay, so make sure you've got that diagram. Now the other one here that's come off says hydrogen fluoride. So let's do HF. Now hydrogen fluoride has got the most electronegative element in the periodic table, which is fluorine. So that is very delta minus. But because it's only got 1 hydrogen atom, fluorine has got 1, 2, 3 lone pairs of electrons. It's got 3 lone pairs of electrons. So you must put all 3 on. But it can only form 1 hydrogen bond because it's only got 1 hydrogen atom. So on a neighbouring hydrogen fluoride molecule, there's a strong short covalent bond. There's another hydrogen fluoride. So it forms a line of hydrogen fluoride molecules, like so. And each hydrogen is electron deficient. So put your dipole on, delta plus, means it's lacking electrons. Fluorine delta minus, hydrogen delta plus, fluorine delta minus, hydrogen delta plus. So you're getting the idea. You must show the hydrogen embedding itself in the lone pair. So I'm going to put some bunny ears on this lone pair here. But don't forget it's got 3 lone pairs. So don't forget on every fluorine, put your 3 lone pairs. The one that the hydrogen goes into. Okay. So there's 1 hydrogen bond. So I'm going to draw a dotted line there. There we go. Dotted line. So there's your H bond. Again, notice the bond angle is between the hydrogen bond and the covalent bond must be as far apart as possible. That's 180 degrees. So you get this line of molecules. Okay, you wouldn't have them bent over because of repulsion. So you should be writing that now into this document. Okay. Now the final one is ethanol, which I already did. But what I'm going to do is instead of drawing all of this out, because it gets a big pain in the neck, I'm going to call that R for the rest of the molecule, R for the rest of the molecule. So don't forget that the rest of the molecule, the oxygen and the hydrogen are at 105 degrees. Why? because there's 2 lone pairs on the oxygen. So it's identical to the hydrogen bonding in water, but we've got this instead of a hydrogen. So this, which is an alcohol, can only form 1 hydrogen bond per molecule, which is why alcohol boils at a much lower temperature than water. But that hydrogen is very delta plus, that oxygen is very delta minus. This is your hydrogen bond. Draw a neighbouring one. There's an oxygen. There's the lone pair of electrons on your oxygen. There we go, lone pair of electrons on your oxygen, which is very delta minus. There's hydrogen bonding between alcohol molecules. But alcohol molecules can only form one hydrogen bond per molecule. So when you put your vodka in the freezer, it actually stays liquid because it can't extensively hydrogen bond like water. So that's your covalent bond. That is your H bond. So my drawings, because I'm trying to draw with a mouse, are a bit rubbish. Hopefully yours, because you're doing it on paper, are a lot better. So that's hydrogen bonding. They're the forces between molecules, and that's hydrogen bonding. Right, it is now 24 minutes past. I'm letting you finish copying that down. And next lesson, which is Friday, we're going to finish looking at these intermolecular forces and hopefully finishing that sheet off. But we're also going to start to look at and introducing you to organic chemistry, because we've now compiled the mock paper, and we want to make sure that we do a little bit of organic chemistry before we do that. So on Friday, we're going to complete this shapes of molecules, these intermolecular forces, forces between molecules. And then we're going to start to look at an introduction to organic chemistry and how you name molecules and so on. So make sure you've got these 4 diagrams drawn. I'm not going to ask you to upload these just yet. I'm going to leave this on the PowerPoint. So I'm going to keep those pictures. And the answers to this sheet, I'm just going to show you where they are now. So we go back. So the answers to these sheets are here, forces between molecules. So you can see that their diagrams aren't as good as mine, because you can't see that bond there is 180 degrees. So that's why I've actually drawn mine on. Now the answers to the rest of the sheet is correct. So if you want to, you can now start to fill in your rest of your sheet to practice your English. Okay, your writing of good scientific language. So here it says, explain the difference in boiling point between these. So you can now start to complete the rest of the sheet. The answers are here. And then on Friday, I'll get you to upload those. So I'm going to leave that on. So make sure you finish copying that down before you leave the lesson. It's dead important you get those diagrams down and not the ones off the answer sheet. Those are the diagrams that go in there. If you can't fit them on there, it's preferable you do them on a piece of paper. Okay. Right. Are there any questions before the end of the lesson? Okay. So just to go back to the classwork. So remember, we are now on week, there we go, shapes. There's the quizzes thing. You can keep doing that. 3 of them have been graded, so you can keep practicing that to improve your knowledge of shapes of molecules. You've uploaded your shapes of molecules. Then those of you who are struggling on amount of substance. There are 2 assignments for you. Those of you who are on A's, you should now be starting to look at the past paper questions, which are here, okay, in preparation for the mock. So I'm going to leave that up for a bit longer. Once you've got it down, you can leave the class. Okay, thank you very much, and I'll see you on Friday.
Wendy, when is the mock?
So the mock exams, we had an email yesterday round from college, and they were asking for 3 scenarios where they're definitely going to be within the first 2 weeks back in January. You're back on the 4th, and the mocks will not start until the 6th of January. And they're deciding, do the second years go first or do the first years go first? Do you have study leave while the second years are doing their mocks? Or do we give you online lessons? So they're just deciding that now. But the mocks are definitely starting on the 6th of January.
Okay.
Okay, and the reason why we're taking them so serious this year, and that's why we're going to do them all in the exam hall and everything, is in the unlikely event that there are no exams and we have to grade you on your mocks. So that's why I'm starting to give you past papers now, so you feel really, you can do really well in the mocks.
Okay.
All right. Thank you. Any other questions?
Bye.
Bye.
Thanks.